Hi everyone, and welcome to Module 3, Part 1. We are at about the halfway point, or we're getting to the halfway point in our course, so that's pretty exciting. For Part 1, I'm going to talk about z-scores, and that really sort of ends our descriptive statistics part of the course, and then I'm going to introduce inferential statistics. Specifically, I'm going to talk about hypothesis testing. So one of the things that we've been doing in learning about descriptive statistics is we've learned how to describe distributions to get an overview of the data for a group as a whole. So how a lot of data points can come together as a data set and how we can communicate about that data set. We've been able to calculate things like mean and standard deviation that allows us to communicate about a lot of people by only talking about one measure or one number. So we're getting that bigger picture. But it's nice to also have a way to work backwards from that. So once we have all of that information about the big picture, about the mean of a data set and how much the scores in a data set deviate from one another, can we then take a single score from a data set and figure out exactly where it sits in relation to the other data for that set? And the way that we do that is by standardizing the score, or by calculating what we call a z-score. So z-scores provide us a numerical framework or a numerical frame of reference for where a score sits in a distribution, specifically in relation to the mean. And we've already been introduced to this when we've discussed standard deviation, but this is a really different way to think about where a score sits in a distribution, how far it is from the mean, above or below. And what we can get is a numerical value that tells us exactly where that score is. So if for a certain population distribution, you have the mean and you have the standard deviation, can you figure out exactly where a single score is going to sit? And a z-score allows us to do that. The easiest way to figure out exactly where a score sits is exactly how many standard deviation units a single score is from the mean. So one of the things that we discussed in the last module is that when we calculate standard deviation, we're only calculating one standard deviation unit. And then certain proportions of our data are encompassed within a certain number of standard deviation units, like we see it with the image on the screen right now. So for example, 68% of our data exists within one standard deviation on either side of the mean. And that's helpful in some ways, but if you have a raw score, you got to do a lot of math to figure out exactly where that score sits if you want to talk about it. But z-scores make it simple. And what's nice about z-scores is that they correspond with those standard deviations that we saw in the last module and that we're seeing on this image here. Z-scores correspond with them exactly. So z-scores are essentially a count, or they're a numerical value that represents the count of standard deviation units. So you'll notice that the z-scores in this image are in red, right below the standard deviations, and they're exactly the same. So a mean has a z-score of 0. That score is exactly the same as the mean. If a score has a z-score of 0, that means that score is exactly equal to the mean. And a z-score of 1.5, for example, would mean that that individual score was 1.5 standard deviations above the mean. The problem with using standard deviation is that you can't really talk about exactly where a score sits unless it's perfectly the same as exactly the same amount of standard deviation units as your standard deviation. And the reality is most scores aren't like that. So if you've got a raw score, it would be nice to have a way where you can say, okay, that score is 1.5 standard deviations above the mean, and z-score is a super simple way to calculate that. So even when comparing individual scores with mean scores, the mean and standard deviation, as we've discussed, are often insufficient to tell us where a score sits exactly in a distribution. Standard scores, or what we're going to call z-scores, help interpret raw scores and make them essentially more meaningful. So the purpose of a z-score is to identify and describe the exact location of every score in a distribution. The definition for z-score is it indicates how many standard deviation units an individual score is from the mean and whether the score is above or below the mean. So to go through this example, we are going to use my cat. This is Kai. You've probably heard her yell at me or talk to me in the middle of me recording these lectures because she's not getting enough attention. But we're going to use her to discuss z-scores to start. So there are two parts of a z-score. First is the sign. So when you calculate a z-score, the number that you get is either going to be positive or negative. And whether or not the number is positive or negative tells you whether or not the score is above or below the mean. If the score is positive, that means it's above the mean. If the z-score is negative, that means the score is below the mean. And then the magnitude of the value. And what that means is when we talk about magnitude in mathematics, what we mean is how big the number is. So the higher the number for a z-score, the further and further away that score is from the mean. And we can see that in this image here. We see those z-scores, they get bigger the further away they are from the mean. And it is regardless of the sign. The sign only tells you what side of the mean the score is on. The magnitude of the number tells you how far away that score is from the mean. So here are some examples. If you have a z-score of 0, that score is exactly the same as the mean. If you have a z-score of 1, that score is 1 standard deviation above the mean. If you have a z-score of -2, that score is 2 standard deviations below the mean. If you have a z-score of 1.35, that means that score is 1.35 standard deviations above the mean. So here's the formula to determine an individual z-score. And you don't need much. It's a super simple formula, but we'll go through it. So we've got z equals x, which we know is score, minus mean divided by standard deviation. So let's go through this. So as usual, what we're going to do is I'm going to show you all the parts of this, and then you're going to know how to solve it from there. So we've got x, and we know that x is an individual's raw score, because what a z-score is doing is it's taking an individual's raw score and converting it to determine where it sits on the distribution. And we can only do that if we know the mean of the distribution and the standard deviation of the distribution, because that's the rest of this equation. M, uppercase M here, stands for the mean of the data set. And then S stands for the standard deviation of the data set. So if we suppose we knew that the population of a particular breed of cat, pretending black is a breed of cat, that have weights that are normally distributed, and we knew that the distribution looked like this. So the mean of the distribution is 10 pounds with a standard deviation of 2. I made this up, please know that, but let's pretend. So we know that the mean here is 10 pounds and the standard deviation is 2. And we're talking about populations. So that means all black cats fall somewhere on this distribution. Where is another thing entirely. But we can use z-scores to determine exactly where that score is. So how many standard deviation units one cat is away from the mean. And so we're going to use Kai to do that. I love Kai, but she's a little bit chunky, all right? She free eats. I recently bought her a timed food dispenser because she's looking a little bit chunky. That being said, I'm a little bit concerned that she's getting a little bit chubby, and while I am very body positive, I want to make sure that she's healthy, but I also want to see exactly what her z-score is compared to the normal distribution of black cats, so I know how far away she is from the mean, how many standard deviation units she is away. So Kai weighs 13 pounds. Let's use Kai's data to calculate a z-score. So we know that x equals 13 pounds because that's Kai's weight. We know that the mean is 10 pounds, and we know the standard deviation is 2 pounds. And essentially what we're going to do is just plug these values into this equation and solve. So when we plug everything in, it should look like this: 13 minus 10 divided by 2. And we're just going to solve. The best thing to do here is to simplify your numerator first. So we're going to do 13 minus 10, and we should get 3. It is totally possible, as we have learned, for a z-score to be negative. So it is totally possible to have a negative value for your numerator when you're calculating a z-score. Okay, so we did 13 minus 10, which is 3, divided by 2. And then you just plug that into your calculator. 3 divided by 2 is 1.50. So what does that mean? Yeah, very good. So a z-score of 1.50 means that Kai is 1.5 standard deviations above the mean. She's 1.5 standard deviations above the mean. She doesn't look happy about it in this photo, but that's just her normal face. So that was simple. We were able to easily find how many standard deviation units Kai is from the mean, and I can compare her individual score to a normal distribution. And that becomes really important when we talk about well-known population data. And we see a lot of well-known population data when it comes to health and when it comes to a lot of metrics, especially in psychology, that are regularly studied. For example, IQ has a normal distribution. So if you knew your IQ and you knew the mean of an IQ distribution and the standard deviation of the IQ distribution for the population, you could figure out how many standard deviation units you were away from the mean by using the z-score formula. So let's try a few more. What I want you to do is use what we have just learned in your notes and find the z-score for an 11-pound cat and for a 6-pound cat. I will wait. Your solutions will be on the next slide. Okay. So we plug this into our formula. 11 minus 10 divided by 2. So that's going to be 1 divided by 2. And we should get a z-score of 0.5 for an 11-pound cat, which makes sense, right? Half of a standard deviation of 2 is 1. And then we add 1 to the mean of 10. And that's halfway between the mean and the first standard deviation. So this cat that weighs 11 pounds is going to fall right here on the distribution. Z-score for a 6-pound cat. Let's calculate that. 6 minus 10. So now we're going to end up with a negative number because 6 minus 10 is negative 4. And that's okay. We want that. Divided by 2. We divide a negative number by a positive number, we get a negative number. So our z-score for a 6-pound cat is negative 2. And that falls right there. So you may be getting to notice how crucial the normal distribution is and how it relates to material we have covered so far. So standard deviations in z-scores are closely related also to cumulative percentages and percentile rankings. In fact, z-scores can be used to determine exact percentile rankings of a data point. Because as we've learned, how this bell-shaped curve worked is exactly in the middle of that bell-shaped curve, as we can see in this image, is our cumulative percentage of 50%. So the exact middle where we would draw the line down it to split it symmetrically in half is 50%. And what that means is that 50% of individuals in this distribution have the score that sits in the mean or below. And we learned in the last module that the mean, median, and mode are exactly equal for a normal distribution. So the mean and the median and the mode are the exact same number. So z-scores are particularly useful because you get a very exact percentile ranking. In our first module, when we learned how to calculate percentile rankings, those were approximate percentile rankings. Z-scores let us get very, very specific. And this is how we see z-scores in the real world. So let's figure out how to determine percentile ranking from a z-score. One of the things that you are now going to start encountering, and this is the first module that you will do this, are all of these student tables. And these student tables are essentially tables that were created by people who are much smarter than I am, that students who are calculating statistics by hand use to determine things like percentile rankings, statistical significance, etc. So this is our first one. In this module, you have a file that's called the table of the normal curve. And using that table, you can find an exact percentile ranking if you have a z-score. There are two tables for the normal curve. The table that you're looking at right now is the table for negative z values. There's a separate table for positive z values that I will show you in a second. So this is our table for negative values. If you have a negative z-score, you're going to look for the table that says negative on it. And you'll notice that the column that says z at the top all has negative numbers, so that's our clue. Let me show you how to use this table. So say, for example, we had a z-score of negative 3.33. The way that this table works is that you take that number and you break it into two parts. You have the negative 3.3 and then the 0.3. If you added those together, you would get the negative 3.33. But the way this table works is to find a z-score, you have to find the first part of the number and then connect it to the second part of the number, and then find where those two values intersect. We call this a matrix. So we're going to start with finding the z-value row. So our number is negative 3.33. So for the z column, I'm going to look for negative 3, and it's right here. After we find that row, now we're going to find the column that kind of completes our number. So we've got negative 3.3, but our number is negative 3.33. So we have to finish the number. So we're going to look for the column with the appropriate hundredths place. So that second number after the decimal. And that is the column that is 0.03. And that's right here. And then our z-score is literally where those two numbers intersect. So our z-score is 0.0004. And then to speak about that in terms of the percentile rank, you just multiply that number by 100. So we get this. So a z-score of negative 3.33 has a 0.04 percentile ranking. So z-scores can be really useful in these terms, especially when we talk about biomedical research or we talk about things that have normal distributions in the real world. So if I took Kai to the vet, the veterinarian might tell me about Kai's percentile ranking. So what percentage of cats are Kai's weight or below? So what would the percentile rank be for a cat with a z-score of 1.50? Let's figure that out. We know right off the bat that we're going to be using the table of the normal curve for positive z values. You know this because it says positive right on the table, but also the z column is all positive numbers. So as I said, we know Kai's z-score is 1.50. First, we're going to find our z-value row, so that's 1.5. And then we're going to finish the number. And for us, the last number in 1.50 is 0. So we're going to use the first column that ends in 0.00. So if you have a z-score that ends in 0, you use the first column that also ends in 0. And then we find where these two values intersect, and that's 0.9332. So we're going to multiply that by 100 to find our percentile rankings. And we get 93.32. And that's Kai's percentile ranking. So 93.32% of cats are Kai's weight or below, which means that she is a bit chunky. But let's find the percentile ranking for a cat that weighs 11 pounds and the percentile ranking for a cat that weighs 6 pounds. Since we already found their z-scores, all we have to do is use the tables to find their percentile rankings. So we know that the cat who weighs 11 pounds has a z-score of 0.50. So first we're going to find our z-value row of 0.5, and then we finish our number and find the column with the appropriate hundredths place, and that is 0. The intersection of those values is our percentile ranking. All we have to do is multiply it by 100 to finish it. So we're going to do 0.6915 times 100, and we get 69.15 as the percentile ranking. Okay, so let's determine the percentile rank of a z-score for a cat that weighs 6 pounds. The z-score is -2. First, we're going to find the z-value row of -2 and then finish the number. Same thing here, it ends in 0. So we just use the 0 column. And then we multiply by 100. And we get a 2.28 percentile. And again, that makes sense too. So that's a score below the mean. So that cumulative percentage is going to be much lower because there's less people. Z-scores are great because they really help determine percentiles for children's height and weight when they're brought to a doctor's office. If you go to the doctor, you can find out your percentile as well. What I'm going to let you do now is get some practice in. I want you to use the data on the slide that follows to calculate Z-scores for each child height and determine their percentile ranking. So this is just some practice for you. So for a population with the following, a mean of 49.50 and a standard deviation of 3.50, I want you to find the Z-score and the percentile rank for each of the following scores. So we've got a mean of 49.5 inches for these children and a standard deviation of 3.5 inches. So I want you to use the formula that you've got on this slide to find the Z-score for all 4 of these. I will have the solutions for you on the next slide. All right. So a score of 55.60, if we plug that into our formula, we should get a Z-score of 1.74. For a raw score of 41.90, we should get a Z-score of negative 2.17. For a score of 38.55, we should get a Z-score of negative 3.13. And you'll notice these are both negative. We want to be extra careful that we keep negative values and we don't lose the negative. One good way to make sure that your work is right is just look at the raw scores. If you have a raw score that's higher than the mean, for example, if you have a raw score of 55.60, that score is above the mean. We know that because it's higher than the mean of 49.5. So we're going to expect a higher number. Therefore, we're going to expect a positive Z-score. If we have a score that's below the mean, like the 2 we just calculated, we should expect a negative Z-score. So those are just little common sense things that you can kind of catch yourself on. And then finally, a score of 51.23. Again, this is a number that's higher than the mean, so we already know that our Z-score should be positive. But also, let's just think about this a little bit. So if we've got a raw score of 51.23 and a mean of 49.50, we're going to expect a really low Z-score because these numbers are very close together. Let's see what we get. There we go. We get a Z-score of 0.49. So that's almost half of a standard deviation above the mean. You can also work backwards with that formula. So if you have a Z-score and you have the mean and you have a standard deviation, you can figure out an individual score by reformulating the equation to look like this. Let me show you what I mean. So if I knew the following, I had a mean of 50, a standard deviation of 10, and I had the following Z-scores, you could actually calculate using this formula the individual's raw score. So I want you to try this on your own. We're not going to do one together. I just want you to try it. Go through these and plug in the value for Z, plug in the value for M, plug in the value for S, and find each individual raw score. So you can pause it, solve these for yourself, use the equation that you see on this slide. Your answers will be on the next slide. Okay, so a Z-score of +1 is an actual raw score of 60. And at a baseline, this should make sense, right? If our mean is 50 and our standard deviation is 10, a Z-score of 1 says that that score is 1 standard deviation above the mean. So the mean plus the standard deviation is 60. 50 plus 10 is 60. So that makes sense. Let's keep going. A z-score of negative 0.5 is a raw score of 45. A z-score of positive 2 is a raw score of 70. And to get wonky, a z-score of negative 1.43 is a raw score of 49.86. So z-scores and standard scores are just another way for us to be able to standardize values so that we can work backwards and forwards in a data set. And it can be very useful, especially when you're converting these things into cumulative percentages or percentile rankings. And that's really how we see z-scores in the real world. Okay, so for the last part of this video, I want to introduce us to inferential statistics. Specifically, we're going to start talking about hypothesis testing. So statistics offers us two ways to determine whether our data either A, show a true pattern from which we can draw general conclusions, or B, if the data that we are seeing is just randomly happening in this particular data set, and if we did the same study again, we wouldn't see the same thing. Statistics allows us to figure that out. Do we have statistical significance? Is the study finding something interesting, or is it just random? Hypothesis testing specifically is a statistical procedure that allows researchers to use sample data to draw inferences about the population of interest. In Module 1, one of the things that I talked about was how in statistics, researchers use sample data to study populations. Hypothesis testing is the step that statistics plays in that process, where it tells researchers, yes, your sample data can be used for the population. It can be generalized back out. So data alone are really not that interesting, but how we interpret data is. So it should be no surprise that statistical analysis supports research at this point, but really once we start talking about inferential statistics, that's really when the experimental sciencey part of this really comes clear. Our last couple of modules, we've been talking about how we take raw data and just organize it in a way that we can communicate it. This part of the process is how researchers answer questions and contribute scientific knowledge to the world. So hypothesis testing is how researchers determine if their experiments worked, if there's a relationship between variables, if two groups that they're studying to see if they're different from one another are actually different, etc. And additionally, it allows researchers to be able to determine, as I said, if the sample data that they worked with can be generalized back out to the population. Hypothesis testing determines if the researcher's results are essentially valid by figuring out the odds that the results happen by random chance. If the odds are really, really low that this is just random, then the researchers can go into talking about their study with a very high degree of confidence that they found something really significant. So the lower the odds, the greater the confidence that something significant has happened. And hypothesis testing allows us to do that. But there's a couple really interesting or important components of hypothesis testing that you have to understand as we move forward. So the first step of hypothesis testing is recognizing two opposing hypotheses. And this is a little bit of like a mind exercise, so bear with me. The first is what we call a null hypothesis, and the second is what we call an alternative hypothesis. So the null hypothesis states that in the general population, there's no change, no effect, no difference, or no relationship, depending on what type of statistical test you're doing. Essentially, nothing has happened. The word null literally means amounting to nothing. And in an experiment, if you were doing an experiment, the null hypothesis would state that the independent variable has no effect on the dependent variable for the population. The null hypothesis suggests that any observed differences between samples is the result of the effects of random sampling or sampling error, and there are no differences between the groups. So even if we saw in our data that there were small differences between our groups, like they had different means for a test, for example, the null hypothesis says Even though you're seeing these little differences between the groups, there's really no difference. There are only differences because of randomness and because of sampling error that those differences exist. The null hypothesis says there's no differences between those groups in reality. When we state the null hypothesis, we identify it by the symbol H subscript 0. The H stands for, predictably, hypothesis, and the 0 subscript indicates that this is a zero effect. Null also literally means of being or relating to 0. So it literally means nothing. It always contains an equality as well. And I will expand what I mean by that. But these are 3 different equalities: equal, greater than or equal to, and less than or equal to. One of the interesting things in research is, and something that as a student of science you may not really understand, is that we always start with the assumption that the null hypothesis is true. So as researchers, we always start with this idea that there is no relationship between our variables. Our treatment is not going to have any effect on our participants. There are no differences between our experimental conditions, etc. We always start from the idea that we're not going to find everything. And the responsibility of the researcher is to provide evidence contrary to that. So it's similar to the concept of innocent until proven guilty that our criminal justice system is designed to support. So the null hypothesis is true until the researchers can prove it otherwise. So when a lawyer goes into a courtroom to give a case, what they are doing is they are trying to prove beyond reasonable doubt that a person is guilty or innocent. And for researchers, what we are attempting to do is provide enough evidence that the null hypothesis isn't true. We are trying to show that there is something that does occur. But we have to start from a place of nothing is going to occur. And then we have to provide evidence and prove otherwise. So if researchers can prove otherwise through their studies and experiments, then they can what we call reject the null hypothesis. And when we reject the null hypothesis, we are rejecting the idea that nothing is happening. So we are saying that something significant did happen. The null hypothesis for this comic would be not a duck. Because what this judge is saying to the lawyer is that, yes, he looks like a duck and quacks like a duck and walks like a duck, but you still have to prove that this is not a duck. So the null hypothesis would be, this is not a duck. We start from the idea that this isn't a duck, and then we try to provide as much evidence as possible that it is a duck, so that we can reject the idea that this is not a duck. Here's some other null hypothesis examples. Cats show no preference for food based on shape. So you would have to do a study that tries to find otherwise, that cats do show a preference for food based on shape. Plant growth is not affected by light color. So your study would be designed to find that plant growth is affected by light color. And age has no effect on musical ability. And your study would be attempting to find otherwise. Yes, music does have an effect on musical ability, etc. The alternative hypothesis is what you traditionally think of as a hypothesis. And the alternative hypothesis is the opposite of the null hypothesis. It says that there is a change, there is a difference, or there is a relationship in the general population. And in an experiment, the independent variable will have an effect on the dependent variable. So you can think of this as an alternative to the null hypothesis. It's literally the opposite. If the null hypothesis is saying nothing happens, the alternate hypothesis says it does. It's identified by the symbol H subscript 1. The subscript 1 essentially just indicates that there is an effect that is occurring. And it does not contain an equality. So it would be does not equal, greater than, or less than. So in this situation, the alternative hypothesis would be that cats do show a preference for food based on its shape. I'm just now realizing how cat heavy this lecture is. You're welcome. So as I said, the goal of research is to demonstrate that the null hypothesis is false. And so when we are talking about research, we always state the null hypothesis, especially in statistics. We state that there is no effect, no difference, no relationship, and then try to show that this is false. Because ultimately, this is about using sample data to make a determination about the population. And we always state the null hypothesis using population parameters. We support the alternative hypothesis by rejecting the null hypothesis. So we're always going to speak in terms of the null hypothesis. At the end of every one of our statistical tests, we're going to figure out if we can reject the null hypothesis or if we fail to reject the null hypothesis. So while it is important to know what an alternative hypothesis is, we're mostly going to be focused on null hypotheses. If we find that our data is statistically significant, which is probably a term that you've heard before, that means we have rejected the null hypothesis. Statistical significance means that we found something in our data. So we can reject the idea that nothing has happened, which is what the null hypothesis suggests. So let's go through an example. So psychologists have noted that stimulation during infancy can have a profound effect on the development of infant rats. Eyes open sooner, there's more rapid brain maturation, faster growth, and larger body weight. So suppose a researcher who is interested in developmental theory or developmental psychology would like to determine whether stimulation during infancy has the same effect on human development. They know that the mean weight for a 2-year-old child is 26 pounds and is normally distributed, with a standard deviation of 4 pounds. So that means what we have here is mu, so we know we're talking about the population. So for all 2-year-old children that are weighed in the United States, they form a normal distribution, and the mean weight is 26 pounds, and scores deviate from the mean, or weights deviate from the mean on average by about 4 pounds. So the researcher knows that. The researcher's plan is to obtain a sample of 16 infants. She's not going to steal them from parents, but she would get informed consent from the parents to participate in this study, and then give the parents detailed instructions about handling and stimulation of those infants. And then again, at the age of 2, they would be weighed. And essentially what the researcher is attempting to find is, do these infants fall within or close to the mean weight of 26 pounds, or are they different? Has there been an effect? So if the mean weight for these children is noticeably different from the mean of the general population, which is 26 pounds, then the researcher can include that increased handling or stimulation does appear to have an effect on development. If it's close to the same as the general population, then the researcher may conclude that increased stimulation does not affect weight. So if we were identifying the null hypothesis, where we start is from this idea that nothing has happened. So even though this researcher created this experiment, asked parents to increase stimulation and do all of these extra things for their kids, but nothing happened. So to state that as a null hypothesis, we would state H subscript 0, and then we do mu, because we're talking about population parameters. The mu of infants handled is still 26 pounds. You see infants handled here, that's a subscript. In statistics, we often use subscripts, and that's just a way that we can know exactly what the variable is representing, and that will become more clear as we go here. So the null hypothesis in this study is that the mean weight of the infants in the study is still 26 pounds. That was where we started from. That's nothing new. That's exactly the same as where we started. That's status quo. So the null hypothesis says that the stimulation didn't work, so that the mean weight of the infants would stay the same regardless of the intervention, which is the increased handling. It didn't work and nothing happened in the study. So that's the null hypothesis. The alternative hypothesis is that the mean weight of these infants doesn't equal 26 pounds anymore. Something has changed. So if it's not equal to 26 pounds, the intervention had an effect. So essentially what we're attempting to do is reject the idea that the kids still weigh the same thing as they do in the general population. Because if they did, then that would mean that increased stimulation didn't have an effect on infant development. So if the researcher found statistically significant evidence that the mean weight for her sample was M equals 30, and this was significantly higher than the population weight of 26 pounds, then the researcher would reject the null hypothesis, because they didn't support the null hypothesis anymore. They supported the alternative hypothesis. And when we support the alternative hypothesis, we reject the null hypothesis. I understand and respect if that is confusing for you right now. As we begin to encounter this more and more, it will become more concrete to you as we go. But it's important to understand this step in the scientific process. So let's go through another example. So research indicates that men rate women who are wearing red being more attractive than when they're wearing other colors. Elliot Niesta did a study on this in 2008, where they found that men were more likely to rate women who were wearing red as more attractive than if they were wearing other colors. So based on these results, Guggen and Jacob in 2012 reasoned that the same phenomenon might influence the way that men react to waitresses wearing red. Their theory is that because men are more likely to rate women who are wearing red as attractive, maybe that would affect how they tip waitresses who wear red. Maybe they tip them more, right? So what they had waitresses do is they had waitresses in 5 different restaurants wear 6 different colored shirts, red included, on different days of the week during a 6-week period. So they essentially rotated 6 different colored shirts for 6 weeks so that they'd be wearing them on different days of the week, etc. Otherwise, they were instructed to act normally. Prior to the experiment, the researchers knew that waitresses' tips from male customers averaged about 16%. So we usually tip in percentages, and waitresses were getting about 16% from male customers on average, with a standard deviation of about 3%. So after the experiment, they calculated the mean tip percentage for each color shirt. So essentially, the researchers were trying to find if the red shirts increased the percentages of the waitresses' tip significantly. So what's the null hypothesis? If we know that the status quo, that average general everyday waitresses are getting 16% on their tips, that's where we start from. That's our null hypothesis. So our null hypothesis is H subscript 0, colon. We would do mu of the red shirt is still 16, because that means nothing has happened. Nothing has changed. So wearing a red shirt for the waitresses did not change their tip percentage. It was still 16%. Nothing has happened. There's been no effect in the study. The red shirts didn't work to increase tips, essentially. The alternative hypothesis is just the opposite of that. So if the null hypothesis says that the mean equals 16, the alternate hypothesis says that the mean doesn't equal 16 anymore. So something has changed. So if the researchers find that male customers tip waitresses the same amount, regardless of what color shirt they are wearing, the researchers will fail to reject the null hypothesis, because the null hypothesis is still true. So if they finish their study and they calculated the mean percentage that waitresses received on the days they wore red shirts, and the mean percentage was still 16%, then the red shirts didn't work. The null hypothesis is still true. So therefore, we failed to reject it. The ultimate goal is to reject it. And if we don't accomplish that, we fail to reject. Like if you had to go to the grocery store to buy milk and you bought a lot of candy and cookies and a couple bananas and did not buy milk, you would have failed to have bought milk. Same thing works for this. But if the researchers found that male customers tipped waitresses more when they are wearing red shirts, the researchers will reject the null hypothesis. So if at the end of the study, the researchers found that waitresses who wore red shirts were getting tipped at 20%, that is different than 16%. So we did find something. The red shirts did have an effect. So we can reject the null hypothesis that states that there is no effect. And essentially, that is our ultimate goal in inferential statistics. For this module, we're going to learn how to calculate a correlation. And every time we calculate a correlation, I'm going to show you how to figure out whether or not we can reject or fail to reject the null hypothesis. But it's important to have a baseline understanding of what that really means. I will see you for part 2.